Alright guys, we want to talk about the Doppler effect, which is another phenomenon involving waves in a medium. And so when we think about a wave, after that wave crest leaves the source, the motion of that wave is governed by the properties of the medium. So in other words, it doesn't matter what we do with the source, the motion of the source cannot affect a wave that's already been emitted. We want to talk now about the situation where we have a moving source. Okay, the source is producing waves and it's also moving, or we can also think about the situation where we have a stationary source and an observer moving relative to the source. So let's consider the case for a moving source emitting sound waves. And here's an animation that shows that. We have the light blue dot as a source. It's moving to the right. It's emitting sound waves that propagate with a constant wave speed v. And as they propagate along, we notice that those wave fronts tend to stack up over here on the right hand side. So to an observer standing in front of an approaching observer, we observe a higher frequency or a higher pitch of the sound because these wave fronts stack up on each other because the source is moving as these wave fronts are emitted. Now if we were to stand behind a moving source as it's moving to the right, okay, so we have a receding source in this case, an observer over here finds these disturbances in the wave. These wave fronts are further spaced, the wavelength is greater, the frequency is lower, so an observer on this side of a moving source hears a lower tone. And so this is why if we are standing on a street corner and someone is honking their horn, we hear a high pitch at first, and then as the car passes, it switches to a low tone, and that is called the Doppler effect. So the change in frequency when a source moves relative to the observer is called the Doppler effect. And just to solidify what we talked about here, if the velocity of the source is to the right, okay, in front of the source, or with an approaching source, we hear a higher apparent frequency or pitch, and behind the source there's a lower apparent frequency or pitch. I want to talk about a special case, and that is if the velocity of the source is actually greater than the speed of sound. So here's an animation that shows that our source is really moving here, and you can see it's still emitting waves, but it's getting out in front of them. And right behind the source we end up with a lot of wavefronts, which means there is a large disturbance in the air behind the source, and this is called a shock wave. And in the case of an object moving faster than the speed of sound, it has a little bit more familiar of a name. That's right, the sonic boom. So this structure here, this shock wave caused by when an object is moving faster than the speed of sound in the medium that it's in, this shock wave that's produced is called a sonic boom. And I think this is a cool visualization that really shows you the turbulence in the air, this wildly varying disturbance in the air directly behind the quick moving source. Returning to sources moving at subsonic speeds, we have the four equations here for Doppler shifted waves in a medium, and in this case we have two different sets of equations, one for a stationary observer and one for a stationary source. And this is because with a wave like a sound wave, there's a medium involved, and so the motion of the observer relative to the medium and the motion of the source relative to the medium affects the overall form of the Doppler shift. So I state these four equations without proof, but I do want to point out a few details about them. First of all, if the source is approaching, the wavefronts are going to pile up and the frequency is going to increase. So this denominator here includes a minus sign because we want to increase the frequency of the source for the Doppler shift due to an approaching source. For a receding source, we have a plus sign in the denominator because the frequency is reduced. Those wavefronts stretch out into space as the source recedes, and so the frequency heard by the observer is less than the original frequency of the source, so we have a plus sign here, and the denominator is greater than 1. For a stationary source, we have the same relationship. Once again, if we have a approaching observer and a stationary source, the frequency is going to be increased. And if we have a receding observer from a stationary source, the frequency is going to be decreased. For light, the situation is a little bit different because light travels at the speed of light. And as we approach the speed of light, the rules about velocity change a little bit. And so these two formulas were derived from Einstein's theory of special relativity. And so if we have a receding source, meaning the source is moving away from us, in that case those wavelengths get stretched out into space, and so they appear longer. And so in that case we have a minus sign in the denominator is going to increase the wavelength when we have a receding source. And this is called red shifting. The light is red shifted because red has the longest wavelength of the visible spectrum, and so if the wavelength is increased, it's shifted towards the red. For an approaching source, those wavelengths pile up, the frequency increases, the wavelength is reduced, the effective frequency I should say, the wavelength is reduced, the approaching source, and so if the wavelength is reduced, it's shifted towards the blue region of the visible spectrum. Blue has the shortest wavelength of all of the visible light, and we have a positive sign here in the denominator because we are increasing that. Excuse me, we have a positive sign here in the denominator. A bigger denominator means we are decreasing the length of the wavelength, and this is called blue shifting the light. So the reason I point out all these sign changes is because on your equation sheet, you're only going to get 3 equations. One for when we have a source which is moving, V sub s appears in this equation. One for when we have an observer that is moving, V sub o appears in this equation here. Okay, and then whether we choose the plus sign or the minus sign depends on if the frequency is increased or decreased, and so that relies on your interpretation of the physics. If we have an approaching source, we expect the frequency to be increased, so we would choose the minus sign here, and similarly for a receding source. For light, we also have these plus-minus relationships here. If we want to blue shift the light and reduce the wavelength, we want a plus sign here. A bigger denominator is going to blue shift it. A minus sign here is going to red shift the light. So these are the 3 equations that's going to be on your equation sheet. I'm going to do an example involving Doppler shift of sound in the next video, and I hope these slides were useful for you guys.